Yeah, in the last session I had given you a overview of how the retrieval augmented generation happens. Now we are going to get into the specifics of how to make it happen and how to write LangChain code in order to make that happen. So we are going to go very methodically and slowly and ensure that you are able to understand each step of this process. So to start with, I have a more elaborate diagram than what I showed you on the other day. So this is the working diagram that we are going to use in order to understand how RAG happens. So we start with a bunch of documents. This is the starting documents. Now so this is what we call as our knowledge base, which is a collection of documents on the basis of which we want our LLM to work. So basically you can think that our LLM is basically an English speaking tool. He has been just trained originally in only speaking English and understanding English. Now we are giving him this bunch of documents or this bunch of books to read, and so that he is going to get prepared on these books and he is going to be able to answer questions which we pose on that book or on these collection of books. Now the various steps which are involved here are basically the first step that we do with the knowledge base that we have, the raw knowledge base as we call it, is that we do what is called as chunking. Chunking is basically breaking that document into chunks using what is called a splitter. So we split the documents into pieces and chunks which are manageable, because see, when I have to answer a question, I can't look at all the chunks. So I will look at only a few chunks. In the sense, the RAG mechanism will look at only a few chunks and ask the LLM to create the answer from these selected chunks. So in order to identify these chunks, first of all, the original knowledge base will have to be split into these chunks. Now how do we split it? We will see that in code, how to actually split. Some attention has to be paid to how do you actually split the data into these chunks. These chunks we are calling them as documents here. Now the next step in the RAG cycle is to take these chunks and create what is called as embedded documents from that chunk. So we have to choose a proper embedded model and do it. As I had explained in my original video, embedding basically means embedding will look at each chunk and convert that chunk from its English form to its embedded form. Again, there will be a step called, we will first tokenize the chunk and then convert it into an embedding. So the embedding for every word or every token, embedding is given to every token will be, so first there is tokenization and then there is embedding. The embedding for every token is done very carefully using certain embedding models, so as to, I think I gave you the example last time in my last video where we say king minus man plus woman is equal to queen, something like that. So all of that embedding kind of thing, which is converting a token into a vector, has to happen, and how to make it happen is the job of the embedding model. So all the embedded versions of our original chunks, the chunks are themselves splits of the original knowledge base. So each chunk gets converted into a set of embeddings, and those embeddings are recorded in a special kind of a database which is called a vector database. Now this plays a very key role because it is a database in which I store all the embedded vectors of all my tokens, and I do my proximity search, my cosine similarity search, or my Euclidean distance measurement, or whatever algorithm that I want to use. I have to implement it or I have to use it on the vector database. Okay. So this is all a preparatory activity which I have to do. This is all done before even the user gives a query. So this activity, I would show you this activity. This activity is done before any query is given. because this is kind of loading the vector database with the vectors associated with our data after the data has been chunked. So, this is done first. After that, what happens is that so this is all called pre-production. Okay, this is called pre-production. Now, in production, when the user submits a query, then there is a retriever module which receives that query, whatever the question which the user is asking, which needs to be answered from that data in the knowledge base. When that thing has to be answered, first we take the user query, and once the user query is there, we convert the user query like similar to the original knowledge base using the same embedding model. We convert that data from English form into, of course, first we tokenize it and then we convert it. So, we get the embedded version of the user query. This is the embedded version of the query. This is what happens. Okay. And once the embedded version of the query is taken, then we already have the entire knowledge base already converted into vector form, in the embedded form, which is residing in the vector database. So, this query is then played against this vector database, and at this point various algorithms are used. Some algorithms use k nearest neighbor, some algorithms use cosine similarity, some algorithms measure Euclidean distance, like that different algorithms are used. And what is the purpose of all those algorithms? Find the closest documents or the closest splits which match this embedded query. So, I retrieve the top k similar documents. Now, k, the choice of k also has to be done carefully. If you make the choice k too large, you will have too many documents which will qualify. If you make the k too small, you may miss out some very relevant answers. So, the k has to be chosen, and we will see how to choose k. So, the top k similar documents are retrieved. These top k similar documents are probable candidates from where the answer could be built for this query. The answer has not been built yet. We have just identified the vectors from the vector database, from the knowledge base, which probably will be adequate to answer this question. So, the chunk which is associated with that vector has been identified. That vector is matching, or a bunch of vectors are matching the embedded query. So, based on that, set of documents, a set of chunks have been identified. These are called the top k similar documents. So, when we say documents here, we are actually meaning the chunks there. So, this has been identified. See, if you see, the way the document has been identified is text content. This is the document, this is the vector associated with it, and there is some metadata saying it is coming from the final chapter or whatever. So, that is what is the first step. This is called the retriever part of the RAG. Now, once these documents are identified, there is also quite a bit of work that happens. Now, I am going to emphasize today this part of the work, and then we are going to talk about this part of the work. Now, I am not going to describe this work today, but in general these top k similar documents again are matched with the user query, and an LLM prompt is created and it is given to an LLM. So, after that, based on the user query and based on the similar documents, it is the LLM's responsibility to generate a suitable answer. But I am going to talk about this in more detail in another video which is going to follow this video. Our current session will limit our discussion only up to this, because we are following a divide and conquer strategy, so that we can focus on various steps of a RAG transaction or a RAG retrieval, So I just want you today to understand how the case similar documents are identified and how they are brought out, and after that how the case similar documents are used by the LLM along with the original user query to create a prompt and go to the LLM, and then the LLM will formulate an answer. So that part let's leave it aside for out of today's scope of the lecture. My next lecture will be focused on this part and it will cover how to do this part. Okay. So now we will start looking at how to make this happen. Okay. And I will be doing this live so that each step you understand what is going on. So we just talked about the need for developing a retriever for our RAG LLM. Now I am going to take you through step by step, cell by cell of a Jupyter notebook running on our DGX server, how this code is developed for the retriever part of the LLM. We are going to go very slowly cell by cell so that you understand how to do it, because I would implore you to pay attention to what the way the RAG happens so that you know the pieces and then you can make changes, make adaptations as and when you deem fit. So we are using a bunch of libraries as you can see in Python. Now some of these libraries may be very familiar to you. Here we are using pandas, we are using typing for our data structures, we are using data sets for the working with the data set, matplotlib, and we are using an interesting library which I am sure you have already used once called takdum, which is a library which is used to show the progress, because we just figured out that takadum in Arabic means progress. So that is a good way to remember. Then we are setting some option on the pandas library, but we will come back to that because we are not using pandas right away. Then we are importing some data sets library, and we are going ahead. From data set we are importing a specific class or a specific logic module called load data set. Now look at the way we are using it. So we are creating a data set ds is equal to datasets dot load dataset. Now we are creating the data set here by saying text. We are saying this is a text based data set. The data files right now, our documents which we are originally giving in before chunking are only one document. It is a small document we have taken just to illustrate. You can take a fairly big document, you can take even a book as a document. So the data files which we are using are kmit doc.rtf, only one file we are using. Now at this stage some of you may think you are building a data set and then using it for RAG. From where the hell do you get this data set? In a separate lecture I will talk to you about how do you create these data sets, how do you create the information from the data sets. Now this data set, for example, this data file for example gives some information about KMIT's placement thing picked up from the KMIT website. Now typically what happens is the way these data files are prepared are prepared using what are called web crawlers. So we will at one session talk about what are web crawlers and how do you use data from web crawlers using different packages like Selenium. We pick up data from the internet, then we use different tools, Beautiful Soup and all of that to parse that data and then retrieve it and create these documents. So I will have a session, please definitely we will have a session in which we will talk about how to set up the web crawlers, how to retrieve data. We will talk about Beautiful Soup, we will talk about Selenium, how to pick up data. I will show you how this data can be created. But for this example, let us pretend that somebody else has done this work and created that data for us. And then though we are mentioning split is equal to train, it so happens that when we have created this data set, there is no portion in it which is like typically a data set that you download which is pre-packaged from the internet will have three parts. We will have a training part, we will have a validation part, and we will have a testing part. Any data set that you get from the internet will have these three pieces, but this data set has no such piece. So, we presume that the entire data, though we have indicated the split is equal to train, the entire data is taken as training data. We do not have any validation data at this stage, we do not have any testing data, but you can have. In that case, only the training portion will be sucked into the data set at this stage, and the remaining portion will not be taken, that is the validation data and the testing data will not be taken. So, in the next cell he is printing the data set, and as you can see the data set consists of a class called data set with two columns. One is called the features column or the features attribute, which is of type text, and the number of rows is 1. All of this document has become one row because we did not do any specific breaking up of that or anything. Now our data set is ready. Now what do we need to do? So now we want to convert this data set because it may consist of more than one row. So when though in the present instance there is only one row, but there may be many pieces in this data set, there may be many data files, there may be a list of data files, so there may be many rows. So what we are going to do is all of these we are going to build it together into one LangChain document. So we are going to create one big LangChain document out of this, and that is going to be our raw knowledge base. So our raw knowledge base is basically a list of one document at this stage, and we are going to use the Takadum library in order to work with our data set. So I think this kind of Python statement you must have seen n number of times. What we are doing is, when you see this kind of a construct, what do? You start reading from the for loop. For each document in TQDM, that is a Takadum DS, we are taking each document. In this case we will get only one document because there is only one row here. So we will take one document, and the text version of that document will be the page content, which will be used to prepare the LangChain document, the LangChain document. Now I do not know whether we have talked about LangChain in the past, but LangChain has now emerged as the de facto tool chain to work with LLMs or VLMs for that matter. It has become so predominant that almost everybody who is writing applications on LLMs, I am not saying writing LLM, but writing applications on LLM more or less is using LangChain. So it has become a very crucial library to write applications or create applications based on LLMs, which is what we are also doing. So we are creating a LangChain document which is an amalgamation, concatenation of all the documents which come from the data store. In the present instance there is only one document in our data set which we are reading, taking the text portion and creating a LangChain document which constitutes our knowledge base. Okay. So we will look at our knowledge base and we will look at the progress of this. So we are going to run this cell and just understand how it happens, because this is our first real execution cell. We will just say we will print our knowledge base and then we will see how it works, and we will see the progress bar here. We can run it again and just see it in action. Yeah. So the numbers have got updated, as you can see, and so you have said we have read, so we have read 1 out of 1. There is only one document in the data set, so we have read 1, so 100% has been read. See, this bar is coming because of the Takadum library, right. So we are there to see a bar, especially in long running transactions, it is very important, and this document consists of page content which has been concatenated, which is all this, right, which has come from our website, but I have not shown you how to write a web crawler and retrieve this and all that. It is just some content. Okay. So, this is what we have reached up to this point. Now, we will proceed to the next portion and understand how a retriever works. So, our next, we have read the document and the whole data coming from a bunch of documents, in our case only one, is come in and sitting in what is called as a raw knowledge base. So, our raw knowledge base consists of a single lang chain document which contains the whole bunch of data collected from the documents which we have picked up from the data set. So, from the data set we got documents, documents went into a lang chain document. The lang chain document serves as our raw knowledge base. Now, what we are going to do is we are going to split our raw knowledge base into chunks, because when you do vector indexing and embedding and all that, basically we cannot deal with big documents, we have to deal with chunks. Now, for a chunk it is very important what should be the chunk size and all of that, but we will come to that in a moment. Now, here we are doing something interesting. First we are designing a very crude chunking system, and then we will refine the chunking system. After, hopefully you will understand that what is wrong with this existing chunking system. So, first we will present a kind of a flawed chunking, because chunking is very important and it has to be done in a very careful manner. So, we are going to present a somewhat flawed chunking model first, and after that we will see why it is flawed, and then how do we repair the flawed recursive chunking model. So, we will demonstrate this one by one. So, let us see how do you split up a crude chunking model. There is a class which we will use called recursive character text splitter. This is a class, this is coming from the I think from the LangChain library. Yes, from langchain.textsplitter we are importing a tool a module called recursive, you can say it is a function called recursive character text splitter. As you can see, there are two parts of it. One is a recursive character, which I will explain that in a moment, and the second part is easy to understand. It is a splitter of text. It is going to break my text into chunks, that is why it is called a text splitter. Now, why is it called a recursive character text splitter? Is this breaking on the chunks is a very important step. You know, chunks have to be broken, I mean a document has to be broken into chunks in a very careful manner, so that you know, the chunks start making sense. A sense in the sense they are you know, some credible chunks of information. So, there is something called markdown separators which are organized in a kind of a hierarchy. This is above this is above this, and this is above this. Now, I will leave you to understand this. I will just touch upon this and explain how this recursive chunking happens. This is easier to understand, but once you understand this, the rest of the chunks will also start making sense. The rest of the markdown separators also will start making sense. So, the important thing to understand is, so I am basically not looking at these people at the moment. I am looking at only these chaps. So, I am ignoring these for a moment. Okay, but once you understand these are just an extension of that. So, how is this recursive chunking done? So, if I have a big piece of code, big piece of data, imagine this is a big piece of data. First I will chunk, I will split on the basis of this separator. As I said, I am ignoring the above ones. So, I am going to split on the basis of this separator. What does this represent? This represents a double line, a line and another line. There are two line separators. So, let us imagine that I have this chunk and I have this chunk, and there is a double line in between, double line spacing is there in between. So, the first time the chunking will be done based on the double spacing. Now, after I have done this splitting, let us say this chunk size is still big, okay, and this is okay, okay. After I have done this, the split based on this chunking, this is very big and this is okay, this size is okay, that is it is within the maximum chunk length. So I will specify the maximum chunk size here, but let us say this has fallen below the chunk size, whereas this is not, this is still bigger than that. So this is bigger than this 1000. So what do I do? Now suppose there are no double lines in it, in this chunk there are no double lines, right. If it was double lines, I would have split it in the beginning only on double lines. Now what do I do? Because this is still big, I split it on the basis of a single line. So I take a single line separator, that is a line separator, and try to break it into lines. Okay. Now it may so happen that one of the line is still bigger than the chunk size. So let us say this line is okay, it has come below the chunk size, whereas this line is huge, it is still greater than chunk size. Okay. Then what I will do? I will do separation, actually I will do next time the separation based on the dot on the period, that is the end of the sentence. So that is the separator I use, but he has used a space separator. So then I have to separate this based on spaces and then think that has it gone down to the chunk size. Obviously if it is spaces, unless the words are too big, it would be broken down and we will get chunks which are very small. So that is not a very good idea, but you may not come to this level. So normally you will stop at this level, the chunks will reach the correct size, because all these are different chunking mechanisms. For example, here if you see, this is up to 6 line spacing, 1 to 6 line spacing, that kind of spacing. This is for example spacing in which there are all these hyphens, star spacing, stars and new lines, hyphen and new lines, underscores and new lines. These are all different kinds of breaking you can do. These are the separators, these are called markdown separators, but they are organized in a recursive manner, first this, then this, then this, then this. So they go in that manner. So I think this is what is called recursive character text splitter. So first split from top down based on the highest markdown separator, first try to break the chunk. If the chunk has not come below the maximum chunk size, break it further, then break it further till it goes below the chunk size. Okay. So I have tried to elaborate it in this manner. Now let us see this in action. Now this is flawed and we will soon discover why it is flawed. So text splitter is equal to recursive character text splitter, chunk size is equal to 1000, that is the maximum size of the chunk which can be accommodated is 1000. Okay. Chunk overlap is normally 10% of the chunk size, because very often what happens is during embedding and otherwise also in chunking, what may happen is when you break a sentence, when you break a chunk at a particular size for example, or at a particular point, it may not make sense, so we need some amount of overlap which is required or which may be needed. So anyway, we will talk about that overlap a little later, and so there is a need for an overlap between chunks. So during breaking, then add start index. So this will create each chunk and give us those chunks from the text splitter which we can read. And do you want any metadata to be also recorded with each chunk? Like for example, the character start index, the chunk start index, that is this chunk is beginning at this particular position. We need it because at a later point during question answering it may be useful to say where is this chunk beginning in the whole original document. So in the whole lang chain document, where does this chunk start? So it might be useful to remember this along with the chunk as part of the metadata of the chunk. So I said true here. Strip white space from the end of the document, yes, all the white space which is there, if at all it is there at the end of the document, that may go off. And I am giving the list of separators, this is the list of separators in a hierarchical manner, in a precedence manner, that is called the markdown separators. So I have supplied all the separators here, and this is how I have created the splitter. So what does the splitter do? It breaks the original lang chain document, which remember is the amalgamation of all the data that we have collected. Now we are breaking it down into pieces called chunks, but we have a restriction on the maximum size, and there is a mechanism to chunking it, which is using the markdown separators, which I illustrated. This is the concept. So that is what is happening, and let us go down a bit and see what happens after this in the code. These 3 lines over here are going to build the chunks, or going to build a list of chunks. So see this, for doc in raw knowledge base, there is only one doc in the raw knowledge base. Docs processed is equal to text dot splitter split documents in that doc. So we are calling the split documents. The split document is what we just wrote, no? That is a split documents doc. So we are calling it on the, no, this is the text splitter which we had. This is the class. We instantiated this class recursive character text splitter with all these parameters. On that we are calling a method called split documents. So this is the split document method which is already available on the recursive character text splitter instance which we have created, and we are given the doc as the parameter to take this doc and split it. So it will give docs processed with that chunk size. So let us print the lengths of docs processed to see whether we got a chunk bigger than 1000, or we will play a little bit with that and just demonstrate what happens. So we will just introduce a cell here just to illustrate, so that we can print and check. We will print the docs processed, the list, that is pretty straightforward, and let us print the length of there are 4. So because the chunk size was I think 1000, this document was split into 4 chunks. In fact, you can see the start indexes in the code above. We have probably no docs processed. Can you come down? And there is that metadata also. This is the start index which has come. There is start index here also, there should be 4 times. So that is all the metadata which is also got recorded. There is initial start index of 0, this is the first chunk, then there is a second chunk, and then there is a fourth chunk, third chunk and a fourth chunk. So that those are the chunks which are there, and they have been recorded. As you can see, there are 4 chunks which it has been made into. Now this chunking, we just talked about how the chunking happened, but this chunking is not very good. Reason is, okay, now in order to appreciate why this chunking is not good, let me now elaborate. Again, as I said, you need to understand the conceptual framework behind all this, not just take this code and try to run it. It does not serve any purpose. Now what is the mistake we have over the chunk size? Okay, now some of the chunks may be small, some of the chunks may be big, but you know, if we give these chunks directly to the embedding model and ask the embedding model to embed, it is not going to do, because the whole of LLM is based on a certain sequence length, and therefore the embedding also has a limitation of how much should the embedding model look like for data, for a chunk. So if you make it too big, the embedding will fail because the LLM is based on a limit on the embedding, the size of the embedding. So what may happen is, if you give the chunk size as 1000 and your embedding size has been set to 512, then your chunks are going to be bigger than the sequence length of the data, and the embedding may exceed. So it is not good. So that chunk size needs not to be 1000, it should be reduced somewhat. But what should be the chunk size? What should be the maximum chunk size? Let us try and understand the logic behind how to get a right chunk size. Let us talk about that. Now let us move from a flawed recursive text splitter to a more systematic or well designed recursive text splitter. But before that we need to carry out a small experiment, and after that we can design a correct recursive text splitter. Now in our case the data may work with the chunk size of a will work with a chunk size which is much smaller, whereas the chunk size which is given is larger. So basically, you know, our chunk sizes seem to be much smaller, but in real life it may be something else. I will explain what it means. But let us first get something called the max sequence length which our embedding model needs. Now what do you mean by this? See, if you look at our embedding, what does embedding do? Take the original sentence and convert the words into tokens, that is what it will do, and convert those tokens into embedding space. So first we take the sentence, we will tokenize it, and after we tokenize it, tokenizing is pretty easy, it just converts every word into one token or two tokens, and once it has tokenized, each token has to be converted into a vector space where the semantics of that word is captured in the vector space. So that portion where you convert from tokens into vector space is called embedding. So the embedding model has a limit on the number of words or number of tokens, I should say, number of tokens it will convert into vector space at one shot, because there is this whole concept that it has to look at the other words in the sentence also before it gives a meaning, because just the word does not convey the meaning, the word used in conjunction with other words or other tokens also has influence on the meaning of a token, that means on the encoding of the token. What I am saying is, for example, if you say I walked on the river bank, there what I meant, the bank is the bank of the river, and I went to the bank to cash my check. Here the bank is a financial institution. So just the word bank cannot be taken and converted into a vector. The word bank has to be taken in conjunction with the rest of the words in the sentence. So when it looks at the rest of the words in a sentence, and it has to do that while doing embedding, there is a limit on the number of words it can look at or the number of tokens it can look at, either this side or that side put together. So that puts a limit. Now when you have a chunk which is bigger than that, then it becomes difficult to embed that chunk, because you are going to have to embed that chunk after tokenization, but you are going to embed that chunk. But if your chunk is too big and the embedding model can't handle it, then you have a problem. So what we should do? Logically, we should go to the embedding model, whatever we are proposing to use, and ask the embedding model what is the maximum sequence length you can handle, and use that to basically then influence the chunking. So we have to go a little forward and come back. Now this is very important to understand. We can't arbitrarily fix the chunk size as 1000 or something, which we just did. So I will now show you how do you talk to the embedding model and ask the embedding model what should be my chunk size, what should be my largest sequence length. So now I am going to show you the piece of code which will enable me to understand from the embedding model what is the maximum sequence length it can handle. Then I am going to go back to the chunking model and chunking code, that is the recursive text splitter, and set that as my limit. Okay, so how do I do that? Now we have decided to use embedding model called the general text embedding model. There are many embedding models, but we are going to use this GT small as our embedding model. This comes from the people who created it. So I am asking that model using the sentence transformer, because the sentence transformer is responsible for doing something with the model. So I'm asking, that is the way I talk to the model, because some people call the sentence transformer as a process which will use the model. Anyway, right now I am only interested sentence transformer, give the sentence transformer the name of the model, this is the model, I mean this is the complete name of the model, but this is the actual size of the model which I am using. GTE stands for general text embedding, and I am asking for the max sequence length that embedding model can handle, and it will print for me what is the max sequence length the embedding model can handle. Now if my chunk sizes are smaller than that, I am fine, but if my chunks are going to be bigger than that, then my chunks are not going to fit into the embedding model at all. So I have to ensure that my chunks are smaller than that size. In the present instance, you will see, because I am using a very small document and all that, the chunks may be, there are 4 chunks, the chunks are actually smaller. None of the chunks is exceeding the embedding size, but it may happen that it is that. So it is important to know that. So first I find out the chunk size, the embedding model size, then I find out what is the embedding model size which is coming out, or what is the chunk size which is coming out in our case. So let's look at this for a moment. So now what do? I'm also using a tokenizer, because finally the size is measured not so much in the number of characters, but in the number of, or not so much in the number of words, but it is measured in number of tokens. Now as we talked about earlier, a token and a word can be used by and large synonymously, but generally I would say 4 tokens become 3 words in general, because some of the words like together are 2 tokens, not 1, some of the words. So what am I doing? Here I am picking up the tokenizer. First I am using a tokenizer because I want to measure in tokens. Tokenizer is equal to auto tokenizer from pre-trained. Now I am using the same tokenizer. This is nothing but the local version, because we have downloaded it onto our DGX. We have put this tokenizer here, the same model, we have picked it up here. So we are getting the tokenizer from the same model, the embedding model gives us the tokenizer also. So this is the same model, this is same, this is the general name of the model, and this is our local copy of the model. So we are using this embedding model and asking it to give us a tokenizer. So we are saying tokenizer is equal to auto tokenizer from pre-trained, that is from the embedding model give us the tokenizer. Tokenizer is to chop every chunk into tokens. Then we are saying use a tokenizer, and so you see this tokenizer dot encode doc page content for doc in TQDM, that is just to see the progress, docs process. Now docs processed are the actual documents which we processed earlier, you know there are going to be documents there. So in our case I think the docs processed is only 1 if I am not mistaken. So no, but the lengths will come to, for length of after the chunking, what is the length? This is coming post facto. Yeah, after the chunking has been done, what is, so docs processed are the chunk documents, I am sorry, not the original big document, the document which has been broken down into chunks, this is the docs processed. So I am going to measure, I am going to pick up each of my chunk and encode it, that is convert it into tokens, that is tokenize it. So I will say here each chunk is getting tokenized. Tokenize is broken into tokens, and I am getting the length of that for each document, and the collection of such lengths, I am taking the length for each document which has been tokenized, each chunk. Here when you say doc, it means each chunk has been tokenized, and I am taking the length of each chunk and putting it in a list called lengths. So, lengths will consist of about, in our case it so happens, based on the spacing and based on the double line and single line and all that, it looks like our document will be broken into 4 chunks, and we will know what are the lengths of each chunk in number of tokens. Remember, chunk is going to be tokenized, and then we are using the pandas series histogram logic. So, we are creating a series out of the lengths list. This is how you create a series and draw a histogram. Histogram is what? It just shows the frequency of occurrence. So, once we do that, we are labeling it and we will run it and see it. So, we will get 2 pieces of data. We will see one, the histogram of our thing, and also the number of the maximum sequence length offered by our embedding model. Let us just look at it and see what is the data we get. So, we are going to run this cell and see how it looks. So, let me just exit from this, and so that we can run it nicely and see what happens. We are going to run this cell. Yeah, this is the output that we get. Actually, there are 2 pieces of the output. Can we see above? Yeah, one output is maximum sequence length. So, let me illustrate this output. So, the maximum sequence length is 512. What does this mean? It means that my model can handle how many tokens at one go? My embedding model can handle 512 tokens at one go. That means the sentence can be 512 tokens big. I can handle that. And what are my actual chunks lengths in tokens? If you come down, I think I will have to erase this and exit this so that he can operate exit, and so my maximum is 512, and what are the chunks that I have? The chunks that I have, there are 4 chunks, as you can see 4 chunks, each is only 1. So, the histogram shows 4 chunks. The first chunk I think is about 150 tokens, second chunk is about 190 tokens, third chunk is about 210 tokens, fourth chunk is about 250 tokens. So, those are my chunks, and there is only one of them, that is why it is showing 1 1 1 1. Each chunk has a different size and we have that many. So, looking at this picture, actually with this data we are fine, because though we said the maximum chunk size is 1000, the actual chunks which came out after the breaking, where the biggest chunk is only 250, which is still not crossing the model size, the embedding model size. But then I am playing a very risky game, because what may happen in real life is that these chunks may be bigger than 512. So, all that information will be lost, because my embedding model cannot embed that information, cannot end up in the vector database at all. So, if it does not end up in the vector database, then all that data is lost. So, I should not do the chunk size blindly as 1000, but I should redesign my recursive character splitter in a more mature manner. This is I am just showing you how you could play with this data and all that, but it is very important that I choose a proper chunk size. Okay. So, now I will show you the improved code, and you will probably be able to appreciate that. So, we will have to scroll down, I think. Oh, we have to exit. Okay. Yeah, so we will scroll down and check what is a better splitter. Okay. Okay. Let's see this code and see what it is doing, a better splitter. Okay. And see how it works. Okay. Now let me explain the good splitter. So, we have created a function called split documents. Now, let us see how that split document work It takes 4 parameters: the chunk size, which we are going to fix very carefully, the knowledge base, which is a list of lang chain document. In our case, I think it is a single lang chain document. Which tokenizer are we going to use? The embedding model name, because the tokenizer name comes from that model name. So we have to choose which embedding model we are going to use, and as an output it is going to produce a list of chunks, which also we are visualizing as lang chain documents. So basically we are dealing in the world of lang chain documents. So our input is a lang chain documents, we are chopping it up or chunking it out, and then creating the smaller pieces which we call chunks, and which is going to be a list of lang chain documents. Okay. Now let us look at our carefully designed recursive chain splitter. What we have done is we have introduced a parameter where we give the tokenizer itself as a parameter rather than having the tokenizer outside. So text splitter, recursive character text splitter from Hugging Face tokenizer. Basically it is a similar character text splitter, only thing is we are using a different module called Hugging Face tokenizer and using it to give us a better text splitter. So we are having a tokenizer which will tokenize the chunk based on the tokenizer name. Then we are going to have the chunk size which is coming as a parameter, which we have to do carefully. The chunk overlap we have fixed it at 10%, add start index we have said true, strip white space we have said true, and separators is equal to markdown separators, which is the hierarchy of separators on which the document is broken into chunks. So this is what it is. So we have had this nice function called split documents. Now let us see how we are calling it. So if we say docs process, these are going to be the chunks which you are going to get after the original document has been broken into chunks. So we are saying for doc in knowledge base, so we are going through each document in our knowledge base, we are only having one. Docs processed plus equal to text splitter, this is the text splitter which we created. On that we are creating split documents. So we are taking these parameters into the constructor of the recursive text splitter, split documents doc as we said earlier. And now what is going to happen, our document is going to split based on this chunk size using that tokenizer. So there are two things which are going to happen. Our document is going to be first tokenized, first broken into tokens, and I mean if you visualize, first the document is going to be converted into chunks, chunks are broken into tokens, I mean that so you need a tokenizer, and all of that is coming into this docs process. So each portion, each chunk is going to come into docs process. Now why do we need a tokenizer? Because we need to be able to see how many tokens are there. Okay. So basically at this stage the tokenization is not so important as breaking the document into chunks. Okay. So the tokenizers is only to help us understand how many tokens are there and all of that. Now we are doing one more step, which is if some chunks are repeated, I guess we do not want them, because the answer can be done from the one chunk of the many. So this piece of code is just some standard Python code where we are eliminating all the duplicate documents if there are duplication of content. So unique text, docs process unique is equal to empty list, go through each chunk for docs in docs process, this is each chunk, that is how we got it. So the chunking has been done, each chunk. If doc page content not in unique test, only then we are making its flag to true on that doc.page content, and docs process unique append doc. So we are getting it added here, and we are, so any duplicate chunks, if the same content is repeated in 2-3 places, they are not going to be used for our processing, they have been removed. So, all of this is basically called the split documents function, which we have written with all these parameters, and then we are calling that at the bottom. So, docs process is a split document. So, this is the chunk size, this is the knowledge base, and this is the embedding model name for which from which we get the tokenizer. So, docs processed is equal to split documents. Now, we choose a chunk size adapted to our model. Now, typically we choose 512 because that is a common model size, as we just saw our model size as 512. Will 512 work for us? Yes, because we saw our chunks were only 250, so it will work for us. And anyway, if our chunks were more, this will be the biggest size of the chunk, because if the chunk happens to be more than 512 tokens, then our embedding will not work and our data will not go into the vector database. So, that is important. Okay. Yeah, the story so far that we have seen, just to do a brief recap, is that we have taken a document and we have broken it down into chunks, and presumably the chunks have been internally tokenized, because when we ask for a size of a chunk, we are interested in actually the number of tokens, not the number of chunks. So, as of now we said two things. One is chunks can be of variable sizes, depends on how the separation has happened, the way the the hierarchy of separators are there. So, they have separated the document on the basis of which chunks can have different sizes. We also said that though chunks can have different sizes, we would like to limit the maximum size of the chunk to whatever the embedding model can handle, because a chunk finally has to be converted into an embedding. An embedding model, if it is of size 512, which is what the embedding model we have, then we should ensure that our chunk size does not exceed 512. Otherwise, that information can never be embedded and can never be converted into a query. So, that is, keeping that in mind, we have to keep the chunks of appropriate size. Now, I took you through an example of improper chunking, and then we followed up with an example of proper chunking, where we measured from the model what is the embedding size, and based on that we decided what the chunking would be. How many chunks would there be in a document? There will be 4 chunks, there will be 5 chunks, or there will be 10 chunks, we do not know, and at the moment we do not care. Now comes the next step, where we have to set up the vector database. If you remember the original diagram, we have been able to do the chunking, but now we have to put these chunks into a vector database using a embedding. Then only the query can be taken and played against these chunks. So, now how do you vectorize it? So, first we have to create an embedding model, and then we have to use the embedding model to create the vector database or the vector store. So, let us get ahead to creating the embedding model. We have already considered the embedding model, but we have not used really the embedding model. We have been concerned about the embedding model only from the point of view of the size which the embedding model can handle, but now we will create the embedding model. So, here is where we are creating the embedding model. Before that, we are going to use a vector database or a vector store, which is called Facebook AI for similarity search, which is called FAS. This is a very important vector store. In fact, most of the applications which I have seen in vector store, there is a quadrant vector store also. We will have some exercises later, I will talk about them, which is a popular commercial vector store, but this is a free vector store called FAS. Quadrant is also available in free open source also, but this is what many people use. So, we have FAS, Facebook AI for similarity search, because we will be doing some kind of similarity search. Then we have the Hugging Face embeddings, we are using that, and we are going to use a distance strategy for comparing documents. So, let us see how we do this. So, my first step is I am creating a embedding model over here. So, let us see how do I go about creating an embedding model. So, first is model name. So, model name stands for the embedding model name, which is that GT small which we have used. Multi-process means that the modeling process, the embedding can happen on a multi GPU kind of a thing. However, here though we are saying multi-process as true, multi-process can also mean some part is done on one GPU, some part of the training can be done on another GPU. Here we are using only one GPU because we are short of GPUs, even though we are running on a DGX, we cannot spare a whole lot of GPU power. So, model keyword arguments are device CUDA 1, that is what we are using. And then we have some arguments for the database for the embedding, which we want to normalize the embeddings. Now, why do we want to normalize the embeddings? Because we are going to normalize them because we are going to use cosine similarity, and cosine similarity needs the data to be normalized, the vector to be normalized, all the vectors will be normalized. So, for that we are saying normalize embeddings to true because our similarity algorithm that we propose to use is cosine similarity. Okay. We will mention that in the next line. So, this is basically creating the embedding model, that is it. It is just creating a embedding model. This is super important because embedding is where the conversion from the tokens into the intelligent vectors happens. So, now we are ready to build the vector database. So, we are building the vector database, the knowledge vector database, which is a vector store where each of the words, each of the chunk is converted into a set of tokens. Tokens are converted into vectors, and all of those chunks along with their data is kept in that vector database. How do we create that? We say we use the files which we have imported from documents. We give the chunks, the tokenized chunks. So, let me put here tokenized chunks. These are the documents process. There may be 4 chunks, 7 chunks, depends on the size of data you are handling. There could be hundreds, thousands of chunks. Then what kind of embedding to convert these tokens into the vector, the intelligent vector, what kind of embedding model we are going to use, which is exactly the same embedding model that you created above, and then to compare the query to the chunk, because when I give a query, the query goes to the vector database and then the chunk is picked up, one chunk is picked up which is supposed to answer the query. There may be more than one chunks which can be picked up, which we will see in a moment depending on your similarity search algorithms. So, once the chunks are picked up, then you give the chunk along with your query to the LLM, which analyzes the chunk, analyzes your query, finds out which part of the chunk is adequate to answer the query, and then creates an answer for the query. But that is the second part which we are not going to discuss in this session, we will take it in the next session. So, here what we are doing is we are creating only the vector database from the documents, which consist of the documents which have already been chunked, the embedding model, and since we have normalized the data already, which was a preparatory step, we are going to use cosine similarity for matching a user's query to a chunk or a set of chunks. So, I think this should clear the basic story of building the vector database. So, now we have chunked the documents, we have done their embedding, and we have put them in a vector database. So, the data has gone into the vector database. So, that has already happened. So, now we are ready to move to the next stage. So, let us now go to the next stage. So, before that, let me just erase this part and exit this so he can scroll. Okay. So, let us go to the next cell, which is yeah. So, now we are going to just demonstrate in this session how do we use a user base, how do we use the knowledge vector database. So, this should tell you how we do it. So, if I give a query let us say I formulate a user query. This is I have formulated a user query, I think. Let me do this again. So, I am formulating a user query. Now, I have some data, some document, you will be given that document, so do not worry about it. So, in that document, how many companies have visited KMIT? Rather, I am asking this question which has to be answered from those documents, which has many chunks. So, user query, how many companies have visited KMIT? What am I doing? Just look at this, look at the right hand side first. I am going to the vector database first. So, the vector DB, I am going to the vector database, asking a similarity search to be performed. Now, moment I say similarity search, I have already defined the strategy for this database earlier, that the similarity search has to be done is cosine similarity. So, I am using the similarity search. Now, the query is going to be this, and K5 means the top how many documents are you going to retrieve, where the search happens successfully. Well, if I am interested, I can do k equal to 5 top k documents, or if I am interested in only the top 2, I can say k equal to 2. So, in this case we have done k equal to 5. So, k equal to 0 or the first document is the most probable document. That is a probability in which the system feels, the knowledge database feels, knowledge vector DB feels that this query can be answered best by this chunk, meaning the embeddings are matching. Finally, it is for the LLM to decide whether this query can be answered from that chunk A, and B, how do you answer that query from that chunk, that is the LLM's job. So, here what we are doing only is that we are identifying whether using the vector database given a query can we go to that right chunk or not. If we can go to the right chunk, then this process, this step is successful, because next the LLM can take the query, take the chunk, and then formulate an answer for that query from that chunk. Okay. So, let us see what are we getting. So, now we are retrieving the document. When we say 0, we are interested in the topmost probability document. That is what we meant by this 0. Retrieve docs dot 0, retrieve docs 0 dot page content. We are getting the page content, that is what is the chunk containing. It will give us in the chunk form. Internally, of course, there are tokens and all that and vectors, but those are used for the indexing. This is the actual data. So, we are asking for the data of the match thing. So, when we ask the question how many companies have visited KMIT, it came up with this thing, with this chunk, which is good. That means it got the chunk right, because using this chunk the answer can be made, because if you see the answer is here. So, using this chunk this answer can be made. Now, at this stage we are not going to create the answer, that is the job of the next stage, where we use an LLM which will analyze this question again, analyze this chunk again and create the answer, right. At this stage we are just going to see whether we can identify the chunk which is relevant to this question. So, looks like it has picked the right chunk. You can see for this question, you see that how many companies have visited, this is the chunk which has been, this is the query, this is the chunk, correct. So, it looks like it has got it right. Our knowledge database, knowledge vector database seems to be working well, and the cosine similarity seems to be doing a good job. Okay. So, let us see with another query whether the story is working, and let us see whether this is there, but before that let me just go out and try one more query. Yeah, here is another query. Let us see what we get here. So, the next query which we gave to the database, to the vector database, is how many students received job offers of more than 40 lakh per annum at KMIT. How many people are there who received such an offer? Again the same story, we are printing the query and then we are going to the vector database, doing a similarity search. Only thing that has changed is the query has changed, right. So, if the query has changed, and obviously the query has to be answered from a different chunk, not the same chunk, then it should throw that chunk as the topmost priority chunk, correct. So, let us see what it printed. So, the question was how many students received offers of more than 40 lakh per annum at KMIT, and then it picked up this chunk where this answer is there. See this is the answer. 06 students received job offers with salary more than 40 lakh per annum. So, this is the chunk and which was picked up, which is pretty good. Answer has not been created yet. Answer creation is the job of the LLM, which is the next stage, this is called the retrieval stage. Then the next stage is called reader stage, where the LLM will be used to prepare the answer. So far we have not used an LLM. So far what have we used? We have used the splitter, we have used the tokenizer, we have used the embedding model, we have used the vector database. Those are the data structures we have used. We have not used the main kingpin of this whole game of building these kind of applications, which is the LLM. The LLM has not entered the picture. The large language model has not, only its trappings and its peripherals have done the job so far, and in our next video we will show you how this thing has to be converted into a sensible answer for the question. We had gone through, we were looking at the development of the RAG, which is the retrieval augmented generation. We had looked at how to tokenize information, how to divide that, first how to divide information into chunks, and the chunks would get tokenized. Then how does that information get stored in a knowledge vector database, how does it get vectorized using an embedded model and get stored. We had also demonstrated that if I give a query, it will identify the chunks which are related to that query. That is very important, because that is the job, that is the first stage of the retriever LLM or retriever portion, because the retriever has to ensure that the search is limited to a few chunks, and now that these chunks have been retrieved, these chunks are given to the LLM along with the original question, and it is the responsibility of the LLM to look at the question and look at the retrieved chunks and formulate an answer. So, now we are going to look at the third stage. So, the first stage was chunking, second stage was absorbing it into the vector database, and now we are looking at the third stage where now that we know what are the chunks which are relevant to the answer and we know the question, basically we will now give the question and the relevant chunks to the LLM and ask it to formulate the answer. So, we are going to show you the coding which goes into doing just that, that is generating an answer given the original question and given the identified chunks which have been identified from the vector database. So, let us now understand how do you set up the LLM for doing that. There are a few more steps which will require in order to get an answer which is suitable, but the first and foremost step is to set up an LLM. So, the LLM which we are choosing to have is this is the LLM. We are calling it a reader model name. I will skip this part. It is the Zephyr 7 billion parameter beta. So, that is the weight, that is the model we are using. Then we have going to give it some data as to how it should go about doing the computation for the model and all that. So, the computation for the model is going to be done using a Quanto config, weights is equal to integer 8. Now, I will just elaborate what it means is that when I talk to an LLM, the weights are there, but when the computation is done, when the inferencing is done, basically it has to do the computations all over again, that is one forward pass has to happen. So, in order for the forward pass to happen on a 7 billion parameter model, the parameters, if they are very big, they take a lot of memory, because 7 billion parameters have to fit into memory. Not only do I have to take those parameters, I have to also do computation over the parameters. So my endeavor is always to reduce the memory and the computation time. Now, one of the techniques we are using to reduce the computation and the memory is, we are going to ask our model that the weights should be quantized, or what do you say, quantization is a process in which the precision is lost beyond a certain stage. So, we are using an 8-bit precision, integer 8-bit precision. We are aware that with this some of the loss may occur, but it may not be very significant, but definitely there will be a loss, but we cannot afford so much of memory and so much of computation time. Otherwise, if we do not do that, if we do not instruct the model to do this quantization, there is a problem that perhaps the model may not run, because the parameters which are used for running the model may not fit into memory. So, because if I say it is 32-bit or if it is 64-bit, it may be difficult to fit so many billion parameters into memory. So, I have to reduce the amount of time, amount of precision for each of the parameter, and we are doing it by using the Quanto configuration, weights is equal to integer 8. We are aware that precision will be lost. So, now we create the model. So let us step through the creation of the model. So, we have model auto, here is where we are creating the model, auto model for causal language model. These are all causal language models, because what is a causal language model? Anything which generates, which causes data to be generated, causes language to be generated, is called a causal language model. Generally, all our text generation models are causal generation models. So, we are giving the name of the model to be created, to be instantiated. Then we are giving the torch data type to be float 38, 32, but the quantization config process, quantization config is process config, which is set to integer 8-bit. That means when calculation is done, we will do 32-bit, but all the storage and all that of the parameters will happen as integer 8, because I cannot afford so much memory. It is going to be done on the CUDA 0 device of our 4 GPU DGX station. So, we have arbitrarily chosen CUDA 0. Then we also need a tokenizer before we can process the data, because remember what is the LLM supposed to do? It is supposed to take my user question, the question, and it is supposed to take the document. So, there is the chunk of the document, not the whole document, but the chunk. So, if it has to do processing on these two, that is the question and the chunk, which has been identified already, we will need to have a tokenizer, because the question will have to be re-tokenized and the chunk will also have to be re-tokenized by the LLM. So, we will need a tokenizer. So, we are having the tokenizer in it. The task is obviously text generation. Now, so this is where we are setting up the pipeline. Pipeline is because there is a tokenizer involved and the model involved. The task is text generation, which means that the generation is going to create an answer, and that answer is part of text generation. Now, we have two parameters, which is called do sample is equal to true and temperature is equal to 0.2. Now, this temperature allows my answer to be either very creative and diverse or very conservative. If I choose the temperature as 1, the answer will be very creative, and if I choose it to be 0, the answer will be very conservative. Now, if I choose it to be very creative, then the factual data will go for a toss, the factual veracity will go for a toss probably, the hallucination there is a danger of increasing. So, I am keeping the temperature as 0.2, but because I am using a non-zero temperature, there will be a probabilistic answer. The answers are always probabilistic, and since probabilistic answers are involved, sampling is necessary. The sampling will be based on the most probabilistic answer. I am sure you know that whenever you are working with a probability distribution, we do not have one definite answer, we have to sample the answer, we have to do a sampling process to procure the answer. So, that goes hand in hand with the probabilistic model. So, I would say that these two parameters would make sense. Temperature 0.2, I want it to be just a little bit creative, and I obviously want sampling to be there. If I increase this too much, I am risking hallucination, so I am not going there. Now there is another interesting parameter which we use for the model, which is called repetition penalty. The higher the repetition penalty, especially after it is 1, you know, when people talk to you, there are some people who are very good at conversation. They don't use the same word for the same meaning again and again. They have a substantial repertoire, substantial vocabulary, and they use different words to say sometimes the same thing or a related thing. Their choice of words is highly nuanced. Now some people are able to do that. Now that is how you influence your LLM to do something like that. Now repetition penalty, that means if the same word is getting repeated again, I make it penalize, I penalize the LLM. So if I increase it to, let's say, 1.5, you will see the LLM will get very verbose in its words, very verbose in the sense very creative in its words. So if you don't want your LLM to become or if you want an LLM to become like a Shri who you know has a very rich vocabulary, what you can do is you can have a repetition penalty of 1.5 or even 2 if you want it to act like Shashi Tharoor, whose vocabulary is very nuanced and very detailed. But if you don't want it, the danger there is he may say something, but the recipient group may not understand what he is trying to say. So we don't want that to happen. So we don't want it to repeat either. So we are keeping a repetition penalty of 1.1. You can play with a higher or lower repetition penalty. I would suggest a little higher for obvious reasons. Now return full text is equal to false because we don't want the return full text. We don't want the full text to be returned. We want only the answer to our question. Max new tokens, that is the answer should be created maximum from 500 tokens. We don't want more than 500 tokens. 500 tokens means what? Typically 4 tokens is 3 words. So you can say I want the answer to come in about 375 words maximum. That is what I am proposing to have the answer as. So this is how I have created the pipeline for the reader LLM, which will act on the chunk and the question. Now I am yet to supply the chunk and the question. So for that I have to create a template, and we will see in a moment how to do that. Now most of the ingredients of our solution are ready. Our question is ready, the chunk is ready, the chunk from which the answer has to be created is ready, and also our LLM has been just prepared. So now what we need is, we need to tell the LLM in a particular way that this is the question and this is the kind of answer you have to give. So we have to give it a prompt which will make it answer the question in the form that we want it to answer. So basically some kind of an instruction template has to be given to the LLM, asking it formulate the answer in this manner, take this question, formulate your answer in this manner and reply to that answer. So reply to that question. So in order to enable the LLM to do this, we have to create what is called as a chat prompt template or prompt chat template, whatever. So prompt in chat format, this is the template. So I am going to say something, I am going to give an instruction to the LLM. So that is the first role where I give an instruction, and then I am going to give some content to the LLM. Remember, I have to give two things, I have to give a question and I have to give the content. First I have to give an instruction, then I have to give a content and I have to give a question, and I have to tell the LLM answer it according to this content and according to this chunk and as per the question. This is something I have to tell. So look at the way I am going to tell the LLM. So this format can change from an LLM to LLM, but by and large it will be something similar to this. So this is called the instruction basically, or some people call it the system role. This is an instruction which we are giving to the LLM, that is called the system role, and this is what we expect the user level interaction to happen, to which the LLM has to give. This is an instruction, this is an interaction. Okay. So, instruction is this and this describes the interaction. So, the instruction is what? I have to give the instruction. So, role and content. Content is the instruction, role indicates what kind of thing it is. So, as you can see there, the instruction I am giving, I am going to give to my LLM is using the information contained in the context. The context is going to be the chunk. Give a comprehensive answer to the question I am going to pass. Respond, in addition to that I am giving some suggestion to the LLM. These suggestions are to be given very carefully. In a later program I will tell you how these suggestions using a prompt injection can be used to screw up the LLM also. So, that is called vulnerability in the LLM. My later lectures we will cover what are these vulnerabilities which you have to do, which you can give, and how to protect the LLM against that. But here we are not doing that, we are just saying respond only to the question asked. The response should be concise and relevant to the question. Provide the number of source document in the sense the chunk. If the answer cannot be deduced from the context, do not give any answer. So, basically the extra information that you are seeing here is we are asking it to also give us information that from which chunk the information has come, something like that. This is not important from a actual user perspective, but since we are playing around with the LLM, we are saying which chunk did you access to get the information. Normally the first chunk or the second chunk will be used because they are the most probabilistic chunks. That is how the chunks have been identified. Then we are saying how it should behave with the question. So, role is user, content is context. This is the context which is in the braces. This is the context which is going to come. This is where I am going to pass the chunk which is there, because using this chunk the answer has to be created. So, I am going to pass the chunk as context. I have given that context. So, this is the placeholder. In our chat template we are using this as a placeholder. This placeholder is going to be substituted by the content, by the chunk which I am going to supply. Now the question is, here is the question you need to answer. This is all part of instruction given at a user level. So, the question is, I am going to pass this question also. So, see there are two placeholders, the context and the question. These are the two I am going to pass. When I am going to ask the LLM to prepare a nice English answer for me, I have to give it a context which is the chunk, and the question which is the question which was asked in the first instance. So, using this template I am going to create the RAG prompt template for using the tokenizer. So, here is the instantiation of the template. This is just a object. Using this object I am creating it just like a JSON object. So, I am creating it RAG prompt template is equal to tokenizer dot apply chat template. So, I am giving this format here as a parameter. So, this is the format of the information. Now, this is an instruction, so it should not be tokenized, because the LLM need not tokenize it. It is an instruction to the LLM that this is how it should give an answer. It is not to be treated as a question or an answer, it is just to be understood as an instruction by the LLM. It is suggesting to the LLM that this is how you should answer the question, this is what are the instructions. So, that is why I have said tokenize is equal to false. Then the question however has to be will be tokenized, the chunk will have to be tokenized. This prompt should not be tokenized because it is only an instruction. Then add generation prompt is equal to true. See, normally after this we also have to add a generation prompt, because you know how large language models work. Unless that generation prompt is there, which is some kind of an incompleteness in the template, the LLM will not be tempted, or LLM will not be forced to produce some new content. And finally, we must know that LLM has been forced to produce new content. So, because the LLM has to be coerced, coaxed, requested to produce new context, I have to say add generation prompt. To this prompt I have to add a generation prompt, that is think of a generation prompt as some kind of a tag which I leave incomplete. I do not close the tag, it is for the LLM to close the tag. So, it prompts the LLM, okay, you do now, okay. So that is what add generation prompt equal to true does. So we are just printing the rack prompt template, though there is no value there. When we print it, we will get something like this. See, role is equal to, if you see, go up, that has become the instruction. Role is equal to system is, come down. So you see, it has become the system tag, and this will be the instruction. This will be the user tag, and it will have two portions, the context and the question. And you see, the assistant has been opened, but the assistant has not been closed. So you will realize that we are not given anything here. So this basically prompts the system to generate something. I have not said what the assistant should be doing. So the chat, so rather the LLM is invited to take the role of assistant and fill it up and give us the answer. So we have given the suggestion here, and this is what came because of the auto generate thing equal to true, add generation prompt equal to true. I guess this is what triggered that. So it will now create that answer, and it will proceed. Okay. Now going down, let us see how we are going to use it, how we are going to engage with the LLM. So these are the, no, this is not the whole thing. Acha, you are showing the whole thing. Okay, let us go piecemeal. I think we are showing it to you again so that you understand the whole story. So we are stepping back a little and saying, this is the user query. Who is Mr. D. Sudhir Reddy? It is our documentation from our document, starting retrieval for user query. Now we are showing you the how the chunk is obtained. So knowledge vector database, that is the vector database which has been created in the earlier lecture for all our chunks for our entire document, vectorized, embedded vectorized. We are doing a similarity search on the vector database using this query, and it might be interesting to note that we are saying k is equal to 2. That is, only the top 2 chunks which are used to fulfill this answer are to be retrieved, not k equal to 5 which was originally there. We have restricted it to k equal to 2 because we believe that there one chunk and perhaps its overlapping chunk, they together are adequate for providing the answer. We do not need more chunks, only 2 chunks may be needed. If you feel that your answer is more elaborate, you can involve more chunks, maybe you can make k equal to 3, k equal to 4, whatever. But since our document is very small, the number of chunks which have to be used to fulfill this answer, which are already identified from the vector database, the number of chunks can be only 2 in our present scenario. So we are printing the first chunk which we can see here. This is the first chunk. So it has a mention of this, but this has only partial information about Sudhir. Some of the other information may be in chunk 1, this chunk 0. So now what we are doing next, now this step is very important, and let us see how the LLM is getting engaged to do that. Actually this is the essence of what I have been talking about. So I will go line by line and elaborate what we are doing here. So you see here, retrieve docs text, we are creating a list, doc.page content for doc in retrieve docs. Now what are retrieve docs? The chunks which were retrieved in the earlier step. How many chunks will there be? 2 chunks only in the present instance. So for all the documents, means all the data in those chunks, some metadata is also there. We are not interested in the metadata associated with the chunks. We are getting those chunks, and the page content of the chunks we are putting it here. So retrieve docs text will contain all the chunks which are relevant. So 2 chunks which are relevant to our search identified from the vector database, they will be identified here. So context, we are setting it something is equal to extracted documents initially, but context has to be concatenated. Remember, this context has to be passed to the question. So, this should include all the chunks which you have identified as suitable for the answer. The preparation of the answer is going to be done by the LLM, but I have to still give it the chunks which are identified for the answer. So, here I am doing a bit of Python. I like particularly this method join, where we are creating the context, which is a concatenation. This I is so that we remember the document 1 or document 0 or whatever. So, we are converting the I after enumeration of the retrieved doc's text into a number form, plus doc, which is the actual content of the document, for I doc in enumerate retrieved doc text. Enumerate is a method which will go to the chunk list, enumerate it and get it out and convert it into document 1 is so and so, sorry, document 0 is so and so chunk, document 1 is so and so chunk. So, that will be the context. So, I hope you have understood the creation of the context. The context will be document 0, the first chunk which was identified as relevant to this query, second chunk which was identified document 1, second chunk which was identified as relevant to the query. Because of the overlap, we have taken 2 chunks. So, I have picked that up, we have picked that, and that is our context. Our question is already there. So, the final prompt is, now we are creating the template. The template has, remember, 2 placeholders, one placeholder for question, one placeholder for context. Context is the chunks, question is the question which I want to ask with the original question. So, final prompt is equal to rack prompt template dot format. Question is, who is Sudhir Reddy? So, I have given the value for the placeholder question, and context will obviously come from here, which is nothing but the documents which have been the chunks which have been concatenated with their 0 and 1 with their indexes. So, my prompt is ready to give it to the LLM. What is the LLM going to do? Look at my question, look at my context, and look at my instruction, which is part of the template, and follow the instruction actually. So, following the instruction means getting the question, playing it against the context and giving me the answer. So, here we go to the most powerful line probably in this whole program, which is reader LLM, the original LLM which we instantiated at the top. We are passing the final prompt, and because it generates a probabilistic answer, we asked it to generate a probabilistic answer because of do sample equal to true. Because probability is answer, we are taking the highest probability 0 of the expected output, because remember it is a generator. So, it generates potential outputs. We are taking the most probable output from the generated text. So, we are taking the most probable output, which is 0, that is the highest probability output, and the generated text which comes automatically as part of the dictionary of the generated output, we are taking generated text, and that constitutes our answer. This is the generated text. How long can the answer be? Maximum of 500 tokens. Who created the answer? LLM. How did it create the answer? Based on our prompt. What did our prompt contain? A question and a context. What is a question? Question is the original question. What is a chunk? Chunk is the relevant data. How did I get the chunk? By vectorizing my information. How did I create the vector? By embedding the original documents. So, this is the long story short of the whole process, and this is the data which got generated. So, it is giving the answer, who is Sudhir Reddy, it is giving a thing, it is mentioned in document 0, document 1, it is making a nice story. In document 0 it is stated he is member of so and so. This is the English which has been created, and an answer has been produced. So, this is what is called retrieval augmented generation, and this is how you do any of this project. The only thing which will change is your original text document. The question will obviously change. So, this I hope gives you a comfort level of how do you develop a RAG on an LLM. This is an important skill, and hope you have understood that skill. In our next sessions, we will introduce another skill which is called a graph augmented generation, and how to go about doing graph augmented generation.